Let's do one last video here in section 10.6. Once again, here's theorem 2 on term-by-term differentiation integration. We looked at differentiation just now, so let's look at integration in this video. And the one I want us to look at, the power series I want us to look at, is the power series for arctangent. Okay, so what do we know about arctangent? Well, we know that the derivative of arctangent x is 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is arctangent plus a constant. So let's write that down. The antiderivative of 1 over 1 plus x squared is arctangent of x plus a constant. Okay, so let's crunch this out. We want to replace 1 over 1 plus x squared with its power series. Now we know that 1 over 1 minus x, we've seen this before. Here's the series for 1 over 1 plus x. It's valid for absolute value x is less than 1. So how do we go from this to 1 over 1 plus x squared? Let's replace x with minus x squared. So everywhere we see an x, we're going to plug in a minus x squared. So this gives us 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot dot dot. And so this is still going to be valid for absolute value of x is less than 1. Okay, and so what we're going to do now is that we're going to integrate this to get arctangent x. So the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. So when we integrate this, what do we get? 1 integrates to x, minus x squared integrates to minus x cubed divided by 3. X to the 4th integrates to x to the 5th divided by 5, minus x to the 7th divided by 7, plus x to the 9th divided by 9, minus dot dot dot. So just keep going here. And then let us have a constant here. But we should realize that for our constant for arctangent here, arctangent of 0 is 0. Plugging in x is equal to 0 makes this whole thing 0. So a itself is going to be 0. And so to finish this off, our formula is arctangent of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9. This power series, if we want to write it in summation notation, it's the sum from n from 0 to infinity of minus 1 to the n times x to the 2n plus 1 divided by 2n plus 1. So hooray, we have this power series expansion for arctangent of x. Okay, so that takes care of this. There's one more thing the textbook doesn't do, and I wish they would have, because there's a really cool little trick you can do here now that you know this power series. And that is, think about, are there any values of x that we can plug in for that would make things particularly nice? So the answer is, well, arctangent of 0, we just plug in, so what are obvious values to plug in? 0 would be an obvious one, but that would just give us arctangent of 0. Well, we know that's 0. This is 0 over here. That's not telling us anything. But what happens if we let x to be equal to 1 here? So this is certainly, it's outside of the range here. It's outside of the range, but as it turns out, the formula is still valid for it. And let's just see what happens. So we end up with arctangent of 1 is equal to 1 minus a third plus 1/5 minus a seventh plus 1/9, so on and so forth. Okay, what is arctangent of 1? Arctangent of 1, this is pi over 4. And so what this says here is pi over 4 is given by 1 minus a third plus a fifth minus a seventh plus a ninth minus 1 over 11, so on and so forth. So rearranging here, we have pi is equal to 4 times 1 minus a third plus 1/5 minus 1/7 plus 1/9 minus ... And so here we have this very cool formula. It says that if you do this series, what is the value of the series? It is pi over 4. This gives us a way to calculate pi. In case you're wondering, have you ever thought about, when mathematicians say pi is 3.14159.265 ... Where is that coming from? Well, there's different series that we can use to calculate out many digits of pi. And so here is maybe the first one that was discovered. It turns out to be not very good from a computational perspective. It bounces around a lot and it takes a long time to converge. But rest assured, it will eventually converge to pi over 4. Just as a little historical note, people think that calculus, we're doing calculus, so people really associate mathematicians like Newton and Leibniz with discovering calculus in the late 1600s. But this particular formula here, this was known to mathematicians in the Kerala School of Mathematics. So Kerala is a region in southern India. My office mate is from Kerala, so he's very happy that I am mentioning this in this video. But this was discovered in around 14 or 1500 or thereabouts. So well before Newton and Leibniz, mathematicians in India had this formula in their pocket. Okay, so that's going to wrap up our videos on section 10.6. Let me just comment that after what we've done so far in the section goes on to discuss power series solutions of differential equations, and we're going to skip that. This is a very cool and powerful thing to study, but it's a little bit outside the scope. This is something that you should study when you hit your differential equations course if you go that far. Either 244 or 252, this is definitely a very good use of power series.